Hello viewers, welcome to the Conicious Tutorials. I'm Sir Amos. Today we are going to look at solving or finding the second solution if one of the solutions to an ODE is already known. And we are going to apply the method of reduction of order to do that. We are going to look at how to use the reduction of order to find the second solution, having known the first solution to the second order ordinary differential equation. Now, the reduction of order simply means we are going to reduce the order of the equation from first order to a second order. And if it is third order, we reduce it from the third order to a second order. So by the reduction of order, if the order is second order, we reduce it to a first order and we are able to solve it. So we are going to take an example and see how we can use or apply the reduction of order to find a solution to find the second solution if the first solution is already known. Now, we learned that if we have two solutions, let's say y1 and y2 to be the solutions to an ODE, then if these are linearly independent solutions, then it means that their ratio, that is y1 over y2, should not be equal to a constant. Or better state should be equal to a function. It shouldn't be a constant. Or the reverse, that is y2 over y1, or y1 over y2 should at the same time not be equal to a constant. It should not be equal to a constant. That means it should be equal to some kind of what? Function. So if this is true, then we say that the two solutions are linearly independent. Now, we are going to apply this knowledge, we are going to apply this understanding to finding the second solution if the first solution is already known. Now, we suppose that if y1 and y2 are the solutions, where we already know y1, we already know y1 as this, then we know that y1 over y2, which in this case our y1 is this. Or writing it this way, y2 over y1, which our y1 is what? Y. So we can leave it as what? y2 over y. The ratio of these ones should not be equal to a constant, but rather it should be equal to a function, and let the function be u of what? X. So in this case, we can make what? Y2 the subject. So y2 will be equal to what? U of x times y1. Or better still, times what? Times y. Now, we already know the y as what? E raised to the power x. So we can fix in the y here. So we have the y2 to be equal to what? U of x times what? E raised to the power x. Now, our y2 will assume the form u of x times e raised to the power x. But we know e raised to the power x. We do not know the u of x. So we need to find the value of the u of what? X. Or we need to find the value of the function u. So that when we multiply it by the e raised to the power x, we will obtain the second solution. So now, how then do we obtain that value? So we obtain that value by applying the reduction of order. That means we have to differentiate this function, that is once, and differentiate again to put it into this equation. Remember, this one is the second solution and it should satisfy the equation. So that means if we differentiate it twice and then we substitute it in here, we should get the same. So let's find the first derivative of this one. So now we are going to have our first derivative to be what? Y prime of y2, and this is going to give us what? Our first derivative is going to give us y prime of y of 2, and so we apply the product rule to differentiate. So by using the product rule, we first first differentiate u. Now I'm going to ignore the x and use only the u, since we have u of x to be the u. Then we maintain e raised to the power x. Then second, I will maintain u, and then I differentiate e raised to the power x. But we need the second derivative. So that means we are going to look for the second derivative. So which is giving us y prime prime. So the second derivative, we will differentiate this one again. So differentiating the first one, we differentiate the u prime again, and we obtain u prime prime. Then we maintain e raised to the power x. And now second, we differentiate e raised to the power x. We are still on this, and then we maintain the u prime. So that will give us u prime e raised to the power x. Now we have differentiated this. We are left with what? Differentiating this, still using the chain rule. But note that u e raised to the power x is the same as this. So we just put in this one as the derivative. So that will be plus what? U prime e raised to the power x plus u e raised to the power x. So the second derivative of the function is giving us this. Now, we know that if we substitute the y prime prime into here, and we substitute the y in, this will give us what? 0. So let's do that. So this implies that we are going to have y prime prime. That is this one. So that will give us u double derivative of u e raised to the power x plus first derivative of u e raised to the power x plus first derivative of u e raised to the power x. But from here we can even simplify it further. So we have e raised to the power x. This and this will give us 2u prime e raised to the power x, then plus u e raised to the power x. Good. So if that is the case, then it means that here becomes what? 2u prime e raised to the power x, then plus u e raised to the power x, and that will be for the y prime. Now minus y, the y is what? The y is u of x. This is what? U of x. So minus u x to be equal to 0. And so when we move forward, we are going to have, u e raised to the power x. So we are going to have this one minusing this one to give us 0. And so we have u prime prime e raised to the power x plus 2u prime e raised to the power x to be equal to 0. Now we have a common term here, we have a common term here. So if we factorize it out, we are going to have this plus 2u prime to be equal to 0. And so moving forward, we are going to have, dividing both sides by this, we have u prime prime plus 2u prime to be equal to 0. And so we have decided to, or we have successfully transformed the equation now into a form of u prime prime plus 2u prime plus to be equal to 0. So this is the point we now need to reduce the order so that we can find the value of what? U. We want the value of u so that when we multiply the u by the e raised to the power x, we will obtain the second solution. So now, to reduce the order, we say that I use w here, so I can decide to use w, or I can decide to use what? M. So I will say let what? M prime to be equal to u prime prime. And that means that M will be equal to what? U prime. If I make this substitution, I will put here what? M prime. So that implies that we have M prime, then plus 2 what? M is now U prime. So plus 2M to be equal to what? 0. And now we have reduced the what? The order from second order to what? First order. And so we can now integrate both sides to find the value of what? M. So that means that we have M prime to equal to what? Negative 2M. But M prime is the same as the M dx. So this will be equal to negative 2m. So it implies that the m will give us negative 2m times dx. And so to obtain m, we take the integral of what? Both sides. We take the integral of both sides with respect to what? With respect to x. And so we are going to have the integral of the m to be equal to negative 2 times the integral of m dx. Okay, sorry. At this point, we need to separate the variables rather. So we have the m dx to be equal to negative 2m. And so we have the m will be equal to negative 2m then dx. So we have to separate the variables. So that means we are going to divide both sides by m so that it will come to the m. Then that means that we are going to have what? 1 over m dm to be equal to what? 1 over m dm to be equal to negative 2 dx. Good. So from here we can take the integral of both sides. So integrating this one, we have 1 over m dm will give us the integral of negative 2 times the integral of what? Dx. So since here the 2 is a constant, or the negative 2 is a constant, so factorizing it out, we are going to obtain negative 2 times the integral of dx. So the integral of 1 over m will give us ln m to be equal to what? Negative 2 times the integral of the x, which will give us what? X. Then plus the constant of integration c. So applying the laws of what? Logarithms. The base of the lane m is e. So the base e will be raised to the power this to give us m. So that means that we are going to have what? M to be equal to e raised to the power negative 2x plus c. And so since this is the same base and the powers are added, that means that we have multiplied with the same base. So that means here can be expressed as 2 raised to the power negative 2x times e raised to the power c. So we can suppose that c, so we let what? C, we let e raised to the power c to still be a constant c. If we do that, or let's say c1, if we do that, we are going to have what? M to equal to what? C1 e raised to the power negative 2x. C1 times e raised to the power negative 2x. Okay, so from here we are gotten the value of m. But don't forget that we made m prime to be equal to u prime prime whilst m is equal to u prime. So we say that but m was equal to u prime. So that means that we are going to have u prime to be equal to what? M, which is c1 times e raised to the power negative 2x. So we change the u prime to the u dx. So we have the u dx to be equal to what? C1 times e raised to the power negative 2x. And the u will be equal to what? C1 times e raised to the power negative 2x. Then times what? Dx. Now at this point, we want to find the value of u. We want to find the value of u. So we take the integral of what? Both sides. So if we integrate this one, then we integrate this one, dx. The integral of the u will give us what? U. And now this one is a constant, the c1. So the c1 comes behind the integral sign, and we integrate only this, e raised to the power negative 2x. So to integrate this, we are going to have c1 times 1 over negative what? 2, or negative 1 over 2, then times e raised to the power negative 2x. How did we integrate this? To integrate this, the e raised to the power negative 2x, we differentiate the power and we divide by the result. So differentiating the power will give us negative 2. So we divide by negative 2 and multiply by the same thing. Okay, so we are going to have this, and u will be equal to what? Let's say negative 1 over 2 c1 times e raised to the power negative 2x. And now we have gotten the value of u, but we can see that the whole of this one. Okay, so from here I'll add another constant, let's say c2. That's the constant of integration. After integrating this part, the constant of integration comes in. So from here, we can see that we have gotten the value of u, which is containing some kinds of what? Constants. So we can assume that the whole of this one is a constant, while this one is also a constant. So if we suppose, so now, if we suppose that negative 1 over 2 c1 is equal to 1, and the second constant c2 is equal to 0, if they assume those values, then it means that the u is now going to be equal to e raised to the power negative 2x. So finally, we have gotten the value of u. We have gotten the value of what? U. Now we know the value of u as this, but initially we said that the second solution, y2, should be equal to u times what? E raised to the power x. This was what we said. So now if the second solution is equal to this, then it means that to get the second solution, we need to multiply the u by the e raised to the power x. So that means that we have y2 to be equal to what? U, which is e raised to the power negative 2x, times e raised to the power x. And so u will be equal to e raised to the power negative x. Sorry, y2 will be equal to e raised to the power negative x. So the conclusion is hence y equal to what? E raised to the power negative x is the second solution. So that is all about using the reduction of order to find the second solution if the first solution is known. Thank you.